Okay, so now let's finally move on to dynamic programming. Are you nervous? Because you should be. Just kidding. Dynamic programming can be really scary for a lot of people, but I'm going to try my best to try to make it as simple as possible. And the first problem we're actually going to be looking at is one we already talked about when we were talking about recursion, and that is the Fibonacci sequence. And this is an instance of a one-dimensional dynamic programming problem. Let me show you what I mean. But first, let's recall what the Fibonacci sequence is. Basically, the 0th Fibonacci number is defined as being 0. The first Fibonacci number is defined as being 1. An arbitrary Fibonacci number, the nth in this case, is defined as being, the n-1 Fibonacci number plus the n-2. For example, the second Fibonacci number is equal to the first Fibonacci number plus the 0th Fibonacci number. Therefore, the second Fibonacci number would be 1 plus 0, which is just equal to 1. And then we could continue calculating the third and the fourth Fibonacci number and continue going just like that. Now, if we wanted to calculate an arbitrary Fibonacci number, let's suppose the fifth Fibonacci number, we would do it using a loop, kind of how I just talked about right now. We would calculate the second, and then we'd calculate the third, the fourth, until we got to the fifth. It'd be pretty straightforward. We could do it in O of n time using a loop like that. What you might not realize is this is actually an instance of a dynamic programming problem. But to really understand the fundamentals of dynamic programming, I'm going to spend a lot of time analyzing it and showing you how we can take the recursive solution that we talked about earlier and convert it into a dynamic programming problem, because that's what you'll normally be doing when you start getting to more difficult dynamic programming problems. So when we solved this problem recursively before, we started with the decision tree. We wanted to calculate the fifth Fibonacci number, and we know to do that, we have to get the fifth minus 1 Fibonacci number, aka the fourth Fibonacci number, and add it with the n-2 Fibonacci number, aka 5 minus 2, aka 3. And basically, we keep drawing out this decision tree until we get to the base cases, which are these two here. So let's continue doing that. For 4, we know we have to get the third and the second Fibonacci number. So for 3, we have to get the second and the first Fibonacci number. And then here, we're going to do the same thing. Notice we're doing the same thing that we did over here. We're going to get the second, the first Fibonacci number. For 2, we're going to get finally to a few base cases, 1 and the 0th Fibonacci number. And for 2 here, we're doing the exact same thing. So this is some of the repeated work that you might be noticing. We're going to get the first Fibonacci number and then the 0th Fibonacci number, and then 1 is already a base case, so we're not going to do anything. We know the first Fibonacci number is by definition equal to 1. Now the only one of these we have to expand upon is this one over here. So 2, again, repeating the exact same thing we already did a couple places. We have to say this is going to be the first Fibonacci number plus the 0th Fibonacci number. Now the code for this approach would look something like this. So we have our recursive function. We know that if the Fibonacci number we're trying to calculate, let's say it's n, is less than or equal to 1, we're going to return n itself. So basically, if n is equal to 1, we return 1. If n is equal to 0, we return 0. If that's not the case, we call our brute force recursive call in both directions. N minus 1 is going to be the left branch, n minus 2 is going to be the right branch. And then, of course, we would get to the base cases, and then, those would return up, and those would return up, and, they would go all the way back up until we got to the root. The downside of this approach, though, is the height of this decision tree is going to be, the Fibonacci number that we're trying to calculate. In this case, it's 5, so the height of the tree is going to be approximately equal to 5. The number of branches is going to be 2. So in terms of big O of n, we would say that the size of this tree is going to be roughly equal to n. I mean, we can see that some of the levels aren't completely filled, but this is a rough upper bound. N in this case is what the Fibonacci number that we're trying to calculate is. But we see we're doing a lot of repeated work here. When we calculated the second Fibonacci number over here, we had to draw out this subtree, this recursive subtree, and then we wanted to calculate the second Fibonacci number again, and we had to draw out the entire subtree. And then, we even had to do that a third time over here. But what's even worse than that is when we wanted to calculate the third Fibonacci number, we had to draw out an even bigger subtree over here. But we didn't only do it once, we had to do it twice. We had to draw out the same subtree over here. So what I'm getting at is there's a lot of repeated work that's going on, and there's a technique that we can use to eliminate this repeated work. It's sort of based on dynamic programming. So this technique of optimization is called memoization. We can basically take a brute force recursive solution. If we see we're creating a decision tree to solve the same subproblem, in this case, calculating the second Fibonacci number, we can cache that. Basically, after we calculate it once, we can store that somewhere so that next time when we're trying to solve the exact same subproblem, we don't redo all of the work. So in this case, we wouldn't even create these subtrees. We would automatically know what the second Fibonacci number is because we calculated it once. So in terms of code, you can see it looks very, very similar to the recursive solution. That's why when you're first learning how to do dynamic programming problems, what people do is they'll solve the recursive problem and then try to add memoization, try to add caching to it. And I still, to be honest, use this technique when I'm solving a difficult dynamic programming problem that I can't figure out. You can see when I call the brute force, I'm passing in 10, but when I call the memoization, I'm passing in 5. Please ignore that. You can consider this as a 5. We're calculating the fifth Fibonacci number using the brute force way. And now with memoization, we're calculating it the memoization way. You can see we're passing in a parameter, which is the cache. Most commonly, I like to use a hash map to represent the cache, but you can also use a array, but I think it's easier using a hash map. So in this case, I'm actually gonna draw our cache as a array because that's essentially what it is. We're mapping a integer. So in this case, a Fibonacci number. So for example, in this case, 2, and we're mapping it to the Fibonacci number, basically the second Fibonacci number. So I'm going to draw it as an array, but we know we're actually using a hash map in this case. So initially we pass in an empty hash map into memoization. So, think of this as the empty hash map. We pass in 5. We're trying to calculate the fifth Fibonacci number. Have we reached the base case? Is this a 0 or a 1? Nope. Is 5 already in our cache? Well, our cache is empty. By the way, this is an O of 1 operation to check if a value is in the cache. That's why we're using a hash map. But we could also use an array and it would be the same time complexity. In this case, 5 is not in our cache, so we call, memoization, or you could call it whatever you want, but we're recursively going to check what the n-1 Fibonacci number is. In terms of the decision tree, we're going to start at 5. Now we're going to check what the fourth Fibonacci number is. We're going to check the same base cases. It's not a base case. It's not already in the cache. Our cache is empty. So then we're going to call memoization n-1. We're going to call the recursive function on 3. And 3 is also not going to execute any base cases. Then we're going to call memoization on 2. This is where things are going to get interesting. So now we're at 2. This isn't, again, quite a base case. It's not in the cache. So now we're going to call memoization on 1 over here, which is a base case. We know 1 is going to end up returning 1 because the first Fibonacci number is 1. Then from 2, we calculate the 0th Fibonacci number. We know that's also a base case, and that's going to end up returning 0. So here we're going to have 1 plus 0. Add those together, it's 1. So we found what the second Fibonacci number is. It's equal to 1. So what are we going to do? We can immediately return it, but we're actually going to cache it before we return it, because what we're saying is we just calculated the second Fibonacci number. If we ever need to calculate it again, which we know we're going to here, we want to be able to calculate it immediately without having to make any recursive calls. So we cache that. So in our cache, for the key value 2, we're going to say the Fibonacci number is 1. Then we're going to get back up to 3. We calculated the second Fibonacci number. Now we have to calculate the 3 minus 1, which is 1, which is a base case. So here we're going to calculate the first Fibonacci number. It's going to end up returning 1. So then we're going to add these two together, which is 1 plus 1. The second Fibonacci number is 1. The first Fibonacci number is 1. Add those together, we get 2. Therefore, the third Fibonacci number is 2. So we're going to throw that in our cache. So for the key value 3, the Fibonacci number is 2. So now we know if we ever have to calculate the third Fibonacci number again, we don't want to have to repeat all this work so we won't have to. And now again, things are going to get a little interesting. Now we're at 4. We calculated the third Fibonacci number. It's time to calculate the second Fibonacci number. We could go through that whole recursive tree, but when we try to calculate the second Fibonacci number now, we're going to check, well, it's not less than or equal to 1, but it is in our cache. 2, the second Fibonacci number, is in our cache. What is it? The second Fibonacci number is 1. So that's what we're going to return. We're not going to do the recursive case. This is a base case. So we're going to end up returning 1. So when we're trying to calculate the fourth Fibonacci number, we get 2, which is the third Fibonacci number, plus 1. So the fourth Fibonacci number is 3, and we can throw that in our cache and then return that up to the parent, which is 5. So now we're trying to calculate the fifth Fibonacci number. We already calculated the fourth. Now it's time to calculate the third Fibonacci number. So we're going to recursively call that, and we're going to see it's not less than or equal to 1. But again, we check our cache and we found it. We found 3 in our cache. The third Fibonacci number is 2. So basically, we don't even have to execute this entire tree. We only have to check 3, and then we immediately find the value, which is 2. So we calculate the fifth Fibonacci number, which is 3 plus 2, and that ends up being 5. So we throw that in our cache. The fifth Fibonacci number is 5, and then we return it. So you can see by caching, this is all the work that we eliminated. So this is actually the size of our decision tree when we implement caching. This is what it looks like. You can see that this essentially is linear. To calculate the fifth Fibonacci number, we calculate the fourth. To calculate the fourth, we calculate the third. To calculate the third, we calculate the second. And to do that, we calculate the first. It's linear. I mean, technically, you can see that each of these nodes actually has a right child, sort of. So you could say that actually the size is not just n, it's 2 times n, but we know that that's also still linear. It reduces to big O of n. So that's the overall time complexity when we implement caching, which is also called memoization, which is actually also called sometimes top-down dynamic programming. This kind of diagram, memoization and caching, is sometimes referred to as top-down dynamic programming because we're starting at the top of the tree and then going down. There's actually another form of dynamic programming, which is generally a bit more difficult actually, because you can't just take the recursive solution and then add caching to it, and it's called the bottom-up approach of dynamic programming. And as the name implies, for this tree, we're going to start at the bottom of it and then work our way upward. So we're still not going to redo all of this work that we, scribbled out, but we're going to start at the bottom of this tree and then work our way upward. And I'm going to show you that right now. So this approach where we don't use recursion at all is sometimes called the true dynamic programming approach. Like some people don't even consider memoization dynamic programming. Some people only consider this to be dynamic programming, but this is also called the bottom-up dynamic programming approach. So we would just pass in whatever Fibonacci number we're trying to compute. Let's say in this case, n equals 5. Here I wrote n equals 10. But to keep it simple, we're going to just calculate the fifth Fibonacci number. So we know we're trying to calculate the fifth Fibonacci number, and recursively we saw that to do that, we have to get the fourth. To do that, we have to get the third, and to do that, we have to get the second. To do that, we have to get the first, and to do that, we have to get the 0th. But why start here, which was the top, and then go top down when we can go bottom up? Start at the base case immediately, and then work our way upwards, because when we have the base case, we can calculate, well, this is another base case, but when we have both of the base cases, we can calculate this guy, and then we can calculate this guy, and then we can calculate this guy until we get to the result that we actually want. So in terms of code, it would be pretty simple, actually. This is the simplest code, I think, of the 3 solutions because it's essentially a loop. Now, it can look a little bit complicated, and that's because I've really optimized this to the point that we don't even need an array, but I'm going to draw it this way just to get the main understanding across. First of all, if we have a Fibonacci number that's less than 2, we're going to return whatever n is. So the 0th Fibonacci number we know is going to be 0. The first Fibonacci number we know is going to be 1. But assuming we have n equals 5, we're going to create, this subarray. I'm calling it DP, and we'll have this as our little subarray here. And now visually, forgetting the code for just a second, visually we would start here, we would want to get the second Fibonacci number. Now, how do we do it? Just take the two previous Fibonacci numbers, add them together. 0 plus 1 is equal to 1. Now we want to get the third Fibonacci number. Add these two guys together. 1 plus 1 is 2. To get the fourth Fibonacci number, add the two previous together. 1 plus 2 is 3. To get the fifth Fibonacci number, add these two together, and we get 2 plus 3 equals 5. We did the result. What was the time complexity? Big O of n. We just had to iterate, n times, roughly speaking. What's the memory complexity? Also big O of n. We're maintaining an array that we have over here. But my question to you is this array even necessary? Every time we got to a value, when we were trying to calculate this guy over here, we only needed the two previous values. And then when we moved, when we calculated that, and then we moved here, we didn't even need those values. We needed the two previous values here. We didn't need this guy anymore. So my question is, do we actually have to maintain the entire array? Or maybe we can get away with only saving the two previous values at a time. And that's exactly what we're gonna do. So for getting this portion of the array here, we only need an array of size 2. And initially the values are gonna be 0 and 1, just like we've drawn over here. But then we're gonna get to I equals 2. We're trying to calculate the second Fibonacci number. We're gonna save this guy in a temporary variable. I'm just gonna write it here. We're gonna save 1 here. And then we're gonna calculate in this position what the second Fibonacci number would be. It's going to be these two guys added together. 0 plus 1 is 1. So what we would do is overwrite this. We know in this case it's, it was previously 1 and it's staying 1, but I'm just doing this to get the point across. And then in the 0th position, we would put whatever originally was over here in this spot. The good thing we saved it here, but in terms of code, we would save it in a temporary variable. So here we would now put 1. So this is telling us we calculated now the second Fibonacci number and put it over here, and then we put the first Fibonacci number over here because we know we're going to need the first and the second Fibonacci number. Now when we take our I, increment it by 1, and try to calculate the third Fibonacci number. And you can probably at this point see where I'm going here, but I'll quickly run through it just to get the point across. So we're going to overwrite the value here now by taking these two original values, 1 plus 1, adding them together, and then putting it over here. So now we have a 2 here. And we would have put the original value, which was 1, and then put it over here. It's already 1, but we're doing it anyway. And at this point, this would be the second Fibonacci number, and this would be the third Fibonacci number. And now here we would take 1 plus 2, add them together, replace this position with 3, and take the previous Fibonacci number, which was 2, and replace this guy with 2. And then these two would be the third and fourth Fibonacci number. And at this point, we've sort of ran out of space, but you probably get the idea. We would now take these two, 2 plus 3, add them together. We would get 5. That's the fifth Fibonacci number. We would end up storing it in this spot. And then we would end up, once our loop stops, which it would now, we would end up returning the value that's stored over here, which is 5. So that's the fifth Fibonacci number. And of course, since we're looping n times, the time complexity is going to be big O of n, but we saved space. We didn't have to allocate the entire array. The space in this case is just an array of size 2, which is constant memory. So our memory is not scaling as we increase our input n. So this is the most efficient way to solve this problem. And I hope this gives you an idea of the thought process that goes behind dynamic programming. Dynamic programming is essentially a technique that takes a big problem and then simplifies it. What makes this a dynamic programming problem is that we have originally a big problem. We're trying to calculate the fifth Fibonacci number. But to do that, we have to solve a sub-problem, which is calculate the fourth Fibonacci number. To do that, we have to solve a sub-problem, which is the third, and another sub-problem until we get to the base cases. So that's what dynamic programming is basically all about. Taking a big problem and then breaking it down into sub-problems, which Fibonacci number is a very good example of because it's mathematically a sub-problem, and then solving that sub-problem. Most dynamic programming problems can actually be represented with equations like this. So this is the one-dimensional case. Why this is considered one-dimensional is because we have a one-dimensional array, which is our solution space, right? We have to get the 0th, 1st, 2nd, 3rd, 4th, fifth Fibonacci number. It's one-dimensional. So that must imply that there are two-dimensional dynamic programming problems, which is correct, and that's what we're going to talk about next.